Underneath every artificial intelligence tool making headlines right now is physical silicon, microchips routing billions of calculations per second through microscopic pathways. For the last few years, the market has treated AI and the GPU, the graphics processing unit, as the exact same thing. If you wanted to build AI, you bought GPUs. The industry is moving past the initial phase of building foundation models. We are entering a period dominated by widespread commercial inference, the actual work of putting those models to use in everyday applications. This stacked bar chart maps out global infrastructure spend. Look at the trajectory from 2023 to 2026. The training block shrinks proportionally, while the capital spend on inference rapidly overtakes it. This creates a physical dilemma. The heavy-duty hardware used to train an AI model is mathematically inefficient for running it. Training requires static, highly predictable linear algebra. Deploying the model into a live business environment requires messy, unpredictable logic routing. Trying to use a one-size-fits-all hardware approach leads to idle compute time, power bottlenecks, and ballooning costs. To understand the fix, we have to look at how data centers were physically built. They were designed with a highly skewed hardware ratio, built for the sole purpose of feeding oceans of data into parallel processors. This 3D schematic shows the standard hardware configuration from the initial AI boom. Notice the bottleneck. You have one single CPU acting as a host node, existing entirely to feed data into 8 massive GPUs, a strict 1:8 ratio. That ratio worked when AI was just a chatbot answering single prompts. But modern agentic AI operates entirely differently. It breaks goals into smaller steps, calls external tools, and runs continuous logic loops to check its own work. That multi-step logic is an incredibly heavy lift for the system. It starves the parallel processors of data. Because the system is bogged down figuring out the next step, those highly expensive GPUs sit entirely idle, burning electricity while waiting. To fix this, hyperscalers are physically rebuilding their systems, moving away from that heavy 1:8 ratio toward an equal 1:1 hardware parity. Agentic AI forces the industry to match specific chip architectures to the exact phase of AI deployment. Let's start with the heavy artillery. The GPU is physically massive, expensive, and the undisputed engine of the current AI boom. Its advantage lies entirely in its internal architecture. A GPU packs thousands of streamlined cores designed to execute data-level parallelism. When you need maximum throughput, shredding through data blocks simultaneously, nothing beats it. But that power requires a massive budget and enormous electricity. And when a GPU handles high-frequency, low-batch tasks, like answering 1,000 separate simple questions, it hits a strict memory wall and loses its efficiency. GPUs are strictly mandatory for training foundation models and running massive batch inference, but they are an expensive mismatch for lightweight, everyday logic operations. For cloud hyperscalers running massive, continuous operations, burning premium electricity on GPUs isn't viable. They need a factory. Enter custom silicon, ASICs, and TPUs. They use a systolic array architecture, hardwiring tensor calculations so data flows in a continuous, rhythmic wave. This locks the hardware design, maximizing performance per watt and making single token generation incredibly cheap. The trade-off is absolute rigidity. You lose flexibility and get locked into proprietary cloud ecosystems. But if you operate standard, repetitive models at a global scale, custom ASICs are the only path to long-term profitability. Meanwhile, the traditional central processing unit, the CPU, is seeing a surge in demand. Modern systems are rediscovering its role as a specialized tool for complex organization. Look at the difference in design. A CPU relies on a smaller number of high-frequency cores built to handle complex logic branching. When an agentic AI workflow pauses text generation to call an API or verify permissions, the CPU manages those unpredictable steps flawlessly. It is highly inefficient at the raw matrix multiplication required to train a neural network, but the CPU is the indispensable orchestrator of the data center. It handles the complex routing so your expensive accelerators can focus purely on the math. Finally, we move out of the data center entirely, down to the physical devices in the real world. This is the domain of the Neural Processing Unit, or NPU. It integrates directly onto system chips inside phones and cars, relying heavily on low-precision integer math. Because memory is kept directly on the chip, an NPU executes localized tasks like voice recognition or image processing in real time, pulling only milliwatts of power. They have strict limits. NPUs cannot handle massive parameter models, and they fail at complex multi-step logic chains. For absolute privacy, zero latency response times, and extreme battery conservation, the NPU is the non-negotiable standard. In the 2026 AI landscape, compute is your revenue. Your hardware has to be optimized for cost per query, not just peak speed. This decision flowchart maps the deployment strategy. The first evaluation point is simple. Where is the AI physically running? If you are on the edge, it splits based on power. Consumer battery devices point straight to the NPU. Local enterprise servers point to the CPU. If your deployment is in the cloud, you have to ask, are you training a model or running inference? Building the foundation goes straight to the GPU. But if you are running inference, the path splits one last time. Raw, high-volume throughput points to the TPU and ASIC. Multi-step, complex agentic logic points back to the CPU. Aligning physical architecture with the specific workload transforms infrastructure from an expensive overhead into a predictable, efficient engine for scaling. The theoretical matrix we just explored ultimately comes down to strict physical manufacturing realities. For hyperscalers and builders of foundation models, the GPU remains your mandatory baseline for training. You cannot bypass it. For cloud operators and SaaS companies, lowering your cost per query requires aggressive migration away from commercial GPUs and onto custom ASICs and TPUs. And for enterprise IT teams deploying agentic tools, stop over-provisioning GPUs. Reinvest that capital into high-end CPUs to manage your logic routing and data flow. The future of artificial intelligence hardware is not a monolithic box of graphics cards. It is a deeply decoupled ecosystem where success depends entirely on choosing the exact right tool for the job.